all of the students. Okay.
Okay, doctor. Thank you very much. I will study, and all of the students they are studying, but we need some questions about the material, and I will send you a message about on Telegram. If you
yes, but please ask me question, okay? Because I cannot enough time for answering you. Okay.
Okay.
Okay. Thank you.
very much.
Thank you.
Thank you very much.
Okay. Which slide we set to you for previous section? Okay, 89. Yes. Okay. So until direct quadrature 0 Q 0 transformation. Okay. I think we set to you until this slide. Maybe this slide. I think. But if you know, said to me, please said to me. Okay, we are ready for starting the lecture. Are you ready, the student? Yes, it's good. Okay. We said to you for previous session about inductance and mutual inductance. Okay, for stator and rotor in synchron machine. Okay, so you see the phi A is relationship to LAA, that is self-inductance of phase A. So this is for psi B for phase B and for phase C in equation of 3.48 and 3.49. And I said to you about rotor circuit equation, and in the rotor we have three winding. One of them is for field, but two winding is for damping winding, or we named by amortisseur circuit or amortisseur winding. Okay. So we said to you about EFD, that is for field of rotor, and that is for damping or amortisseur. This is in the axis, and this is for Q axis. That Q and D is 19 degree ahead of the axis. So Q axis is 19 degree ahead of the axis. Suppose the rotor circuit flux linkages may be expressed as follows equation that you see, equation 3.53 and 3.54 and 3.55, that it's for Q axis field of D axis, and this is for the damping in D axis, and this is for damping flux in Q axis. Okay, now we want to tell you about EQ0 transformation, or that named direct quadrature zero, EQ0 transformation, or named by arc transformation. That arc is the name of people that said to us about transformation. Okay, EQ0 transformation. The EQ0 transformation may be viewed as a means of referring the stator quantities to the rotor side. Okay, axis about referring the all of the inductance, voltage, and current, and etc. Of ABC term to the rotor side, okay, of stator to the rotor. The combined MMF wave due to the currents in the three armature phases travels along the periphery of the stator at a velocity of omega s radian per second. This is also the velocity of the rotor. Therefore, for balanced synchronous operation, the armature MMF wave appears stationary with respect to the rotor and has a sinusoidal space distribution. Since a sine function can be expressed as the sum of two sine functions, MMF to stator windings can be resolved into two sinusoidally distributed MMF waves stationary with respect to their rotor, so that one has its peak over the d-axis and the other has its peak over the d-axis. Therefore, ID may be interpreted as the instantaneous current in a fictitious armature winding which rotates at the same speed as the rotor and remains in such a position that its axis always coincides with the axis. The value of the current in this winding is such that it results in the same MMF on the d-axis as the actual phases currents following in the armature windings. A similar interpretation applies to IQ, expect that it acts on the q-axis instead of the d-axis. MMFs to ID and IQ are stationary with respect to the rotor and act on path of constant means. Therefore, the corresponding inductances LD and LQ are constant. For balanced steady-state operation, ID and IQ are constant. In other words, alternating phase currents in the ABC reference frame appear as direct current in the DQ0 reference frame. The reasons of considering synchronous machine equation in terms of EQ0. One, dynamic performance equations have constant inductances. Two, for balance conditions, zero sequence quantities disappear. Three, for balance steady-state operation, the stator quantities have constant values. For other mode of operation, they vary with time. Stability studies involve slow variations having frequencies below 2 to 3 Hz. Mr. Ahmad Abid, do you have any questions? Mr. Ahmad. Mr. Ahmad Abid al-Rafi'i. Please turn off your microphone. But if you have any question, please write for me. So please turn off your microphone. I can turn off your microphone. Okay. The parameters associated with P and Q axes may be directly measured from terminal tests. So it's good for us to use the term of DQ0. The DQ0 transformation. The equation associated with the stator and rotor circuits completely describe the electrical performance of a synchronous machine. However, these equations contain inductance terms which vary with angle theta, which in turn varies with time. This introduces considerable complexity in solving machine and power system problems. Theta is equal to omega r multiplied to t. The DQ0 transformation can be used to rotate the reference frames of AC waveforms such that they become DC signals. The DQ0 transform, first proposed in 1929 by Robert H. Hart. In analysis of three-phase synchronous machines, the DQ0 transform transfers three-phase stator and rotor quantities into a single rotating reference frame to eliminate the effect of time varying inductances and transform the system into a linear time invariant system. find the position of the rotor relative to the stator reference axis is defined by the angle theta. Each phasor, whether voltage, current, or flux linkage in the stator reference frame ABC can be transferred into the EQ reference frame by projecting one reference frame onto the other using the trigonometric function of the angle theta. The current vectors are ID is equal to KD bracket IA cosinus theta plus IB cosinus theta minus 2 pi per 3 parenthesis plus IC cosinus theta plus 2 pi divided to 3 bracket, and IQ is equal to this equation. If you see the figure, you see, for example, we have, if we have this vector, excuse me, for example, if we have this vector, we can have two vectors in the q-axis and
دخل رقمك شو اسمه اشترى على الساعة.
بس انا ضغطت عليه فتح عندي المال. انت شنو؟ راح يطلع لك
الرقم الاول 14 الفا، الرقم الثاني حذف. الحذفه شو تخلي مكانه؟ تخلي مكانه راح ارد لك بس تكون تحفظها هذا.
Okay. You see in this. So, for example,
اكتب فرضا، شوف سيد اكتب انت، اكتب رقم بالكيبورد، اكتب لا مو صفر.
this vector in the axis is, for example, IA. If this is IA, if this is IA, this is IA cosinus IA.
الدور اروح للارقام، اكتب 5 6 7 بي انت حفظها بي
cosinus theta
كلهم صغار
and this is
الدور ايش تكتب براء؟ اكتب 5 6 7 حول اي بالحقل دوس.
this is IA sinus theta, but it's in opposite of q-axis. This is minus IA Okay.
لا بس على رقم حفظه هذه.
Sign.
ادخل هسه ادخل.
Beta. Okay. We don't have voice. Mr. Salim Nouri, can you hear me now? Mr. Salim Nouri? Excuse me, student, can you hear me? Okay, thank you, Mr. Ali Abdul Hassan and Imam Azir. And so, okay, so you can, if you see the equation, this is IA cosinus theta in at the axis, and this is minus IA sinus theta or sin theta in two axis. Okay. So we have two phase, three phase. One is phase A, phase B, and phase C. Okay, so we have another word or part in the equation about IB cosinus theta minus pi divided to 3 and minus IB sinus theta minus 2p divided to 3, and for C phase is IC cosinus theta plus 2 pi per 3, and for IQ we have another sentences IC sinus theta plus 2 pi per 3.
مو احسن اقول له صوت واضح لو مشتبه. انا بروح متى شلونك؟ شكرا.
It's very important, student. Do you understand?
الامور طيبه، الامور طيبه يقول. الامور قاعد يقرون عم قاعد يقرون الجماعه.
Okay. Okay, thank you.
ما احضر حتى الزينه
So,
والديانه وعلى المحاضرات.
ID and is equal KD, and with another parenthesis, and IQ is equal to minus KQ bracket another sentence. The constants KD and KQ are arbitrary, and their values may be chosen to simplify numerical coefficients in performance equations. In most of the literature on synchronous machine theory, KD and KQ are taken as 2 divided to 3, and this truth will be followed here an alternative transformation with KD is equal to KQ is equal to radical 2 divided to 3 is discussed in section 3.4.8 with KD and KQ equal to 2 divided to 3 for balanced sinusoidal conditions. The peak values of ID and IQ are equal to the peak value of the stator currents as shown below. For the balanced condition, IA is equal to IM sinus omega S T. IB is equal to this equation, and IC is similar than IA and IB, but different in the theta, that is 2 pi divided to 3. Substituting in equation 3.58 gives ID is equal to this figure, that is equal to KD 3 divided to 2 multiplied to IM multiplied to sine omega st minus theta. For the peak value of ID to be equal to IM, KD should equal to 3. Similarly, for equation 3.57, for the balance condition, we have IQ is equal to minus AQ multiplied to 3 divided to 2 multiplied to IM multiplied to cosinus omega S T minus theta. Again, KQ is equal to 2 divided to 3 results in the maximum value of IQ being equal to the peak value of stator currents. Equations above describes a unique transformation from the stator ABC to the rotor PQ reference axis. The reverse transformation from DQ to ABC is not unique, as the two equations above have 3 unknowns, IA, IB, and IC. A unique transformation may be achieved by supplementing the PQ coordinates by an addition coordinate. It is convenient to assume this additional coordinate to be the zero sequence coordinate defined in the same way as in the method of symmetrical components. Under balanced condition, IA is plus to IB is plus to IC is equal to 0, and therefore I0 is equal to 0. So I0 define by the equation of 3.58, that is equal to 1 divided to 3 parentheses IA plus IB plus IC. The matrix of transformation from the ABC phase variables to the PQ0 variables and its inverse. ID, IQ, and I0 is equal to 2 per 3 bracket cosinus theta minus 2 pi per 3 cosinus theta plus 2 pi per 3 minus sinus theta minus 2 pi per 3 minus sinus theta plus 2 pi per 3 and 1 per 2 or 1 divided to 2, 1 divided to 2, 1 divided to 2, multiply 2, the vector of IA, IB, and IC. The law of transformation also applies to stator flux, linkage, and voltage. So, the inverse of the matrix, the part matrix of transformation of PQ0 to ABC is equal to the equation 3.60 that you see this equation.
لا الجيم بيساوي اللي قدامه بعدين مدير الفلوس.
Stator flux linkage in PQ0 components. Using the expression for psi A, psi B, and psi C given by equations 3.47, 3.48, and 3.44, transforming the flux linkage and current into PQ0 components, equation 3.59, and with a suitable reduction of terms involving trigonometric terms, we obtain the following expressions. You see the equation 3.48 in okay, 48. So after that it's the equation 48 psi A, and the equation 47 is psi A. The equation 3.48 is about psi B, and the equation 3.49 is about psi C. So psi D is equal to minus LAA0 plus LAB0 plus P divided to 2 multiplied to LAA2 parenthesis ID plus LAFT multiplied to IFT plus LAKD multiplied to IKD. And psi Q is equal to minus parenthesis LAA0 plus LAB0 plus minus 3 divided to 2 multiplied to LAA2 parenthesis multiplied to IQ plus LAKQ multiplied to IKQ. And psi 0 is equal to minus LAA0 minus 2 LAB0 parenthesis multiplied to I0. Finding the following new inductances, LP is equal to LAA0 plus LAB0 plus 3 divided to 2 LAA2. And LQ is equal to this equation, and L0 is equal to this equation that you see in previous section slide. Okay, this is LAA, this is LAAQ, this is L0. Okay, so LD, LQ, and L0. So LD, LQ, and L0. The flux linkage equation become psi d is equal to this equation. The PQ0 components of stator flux linkage are seen to be related to the components of stator and rotor currents without constant inductances. Mr. Ali Abdullah Hassan Nader, do you have the writing or the okay? Oh, net's very weak. I think my net is or my internet is good, but maybe your internet is weak. Okay, Mr. Ali Abdul Hassan. Excuse me, student. My voice or my picture is weak for another student or no? It's okay, Mr. Haidar. Okay. So, Mr. Ali Abdul Hassan, your internet or your net is weak. Okay. Thank you. The DQ0 components of stator flux linkage are seen to be related to the components of stator and rotor currents without constant inductances. rotor flux linkage in TQ0 components. Substitution of the expression for IDIQ in equation 3.53 to 3.55 gives phi psi FD is equal to LFFD IFD plus LFAD IKD minus 3 divided to 2 multiplied to LFAFD ID. You see, remember the equation 3.6 in previous slide, 3.53. This is the psi FD in the ABC mode, but if we transfer to the PQ0 term, so we are simplifying. So this equation is big equation. Transfer to this equation. That's simplified. It's simplified. So it's good for us. That psi KD is similar to psi FD and psi KQ is similar to another equation. Again, all the inductances are seen to be constant, i.e., they are independent of the rotor position. A stator voltage equation in TQ0 components equations 3.26 to 3.28 are basic equations for phase voltage in terms of phase flux, linkage, and currents. By applying the TQ0 transformation of equation 3.59, the following expressions in terms of transformed the components of voltage, flux, linkage, and currents result. ED is equal to E psi D minus psi Q P theta minus RA multiplied to ID. The term E theta is the above equation represent the angular velocity omega r of the rotor. E theta is equal to omega r is equal to omega s. And the other equation is right in the 3.71 and 3.72. Q and E0. ED is equal to P psi D minus psi Q P theta minus RAI. And another equation is right in below, EQ and E0. The above equations have a form similar to those of a static coil, except for the psi Q P theta and psi D P theta terms that refer to as speed voltage. They result from the transformation from a stationary to a rotating reference frame and represent a phase that a flux wave rotating in synchronous with the rotor will create voltage in the stationary armature coil. The speed voltage terms are the dominant component of the stator voltage. The terms P psi D and P psi Q as the transfer voltage due to flux change in time. Under steady state conditions, the transformer voltage terms P psi D and P psi Q are in fact equal to 0. There are many transient conditions where the transformer voltage terms can be dropped from the stator voltage equations without causing errors of any significance. Signs associated with the speed voltage terms in of equation are related to the sign conventions assumed for the voltage and flux linkage relationship and to the assumed relative position of P and Q axis. Since we have assumed that the Q axis leads the P axis by 90 degrees, the voltage EQ in the Q axis is induced by the flux in the P axis. Similarly, the voltage ED is induced by flux in an axis lagging the P axis by 19 degrees, i.e. a negative Q axis. Therefore, the voltage induced in the Q axis due to rotation is plus omega psi d, and that is the Q axis is minus omega psi q. So So if you see this figure, you see if we have the current for this form, okay, in this. So the flux how the x-axis, for example, is positive. But if the current about the axis the voltage that made by the flux of q-axis is minus. So we have two terms in the equation. For example, this equation 4, it is minus psi q d theta, and for q-axis we have the term plus psi d theta. But d theta is d theta divided to d, or d theta per dt. So because theta is equal to omega r e, so differential of theta per differential d is equal to omega r. Okay, so write here plus omega psi q psi d, and in this term we write instead this equation we write minus omega psi q. Electrical power and torque. In instantaneous three-phase power output of the stator is ET is equal to EA IA plus EB IB plus EC IC. Eliminating phase voltage and currents in terms of PQ0 components, we have PT is equal to 3 per 2 divided to ED/ID plus EQ/IQ plus 2 E0/I0. Under balance operation, E0 is equal to I0 is equal to 0, and the expression for power is given by PT is equal to 3 per 2 parenthesis EDID plus EQIQ. Okay. The electromagnetic torque may be determined from the basic consideration of forces. Mr. Ahmad Avid. Okay. Electromagnetic torque may be determined from the basic consideration of forces acting on conductors as being the produce of currents and the flux. Alternatively, it can be by developing an expression for the power transferred across the air gap. Using equation 3.70 to 3.72 to express the voltage components in terms of flux linkage and currents by recognizing omega r as the rotor speed d theta per dt and we have. It is equal to this equation at this is rate of change of armature magnetic energy. This is power transferred across the air gap, and this is armature resistance loss. Okay, it's very important. So this is for just this. This is rate of change of armature magnetic energy. This is for power transfer across air gap, and this is for armature resistance loss. The air gap torque DE so obtained the air gap torque DE is obtained by dividing the power transferred across the air gap, i.e. power corresponding to the speed voltage by the rotor speed in mechanical radians per second. So you see in this equation is equal to prepare 2 parentheses psi e iq minus psi q id parentheses divided to omega r divided multiplied to omega r divided to omega mechanical. That is equal to this equation that omega r divided to omega mechanical is equal to EF divided to 2. Do you have any question until here? So, excuse me, student, do you have any question until here? Okay. So now is breaking time for 10 minutes. Okay. So we come back to you after 10 minutes. Now is breaking time in class because we want to start a new subject where you need presentation. Okay, so now is breaking time for this session. So you can go and come back after 10 minutes. Thank you, student. Okay, merci then. We come back to you. Are you ready? Okay. Okay, it's good. Do you have any question until now? Okay, thank you. So we start now. Here you need representation. In power system analysis, it is usually convenient to use a per unit system to normalize system variables compared to the use of physical units, amperes, volts, ohms, webers, henries, etc. A per unit system offers computational simplicity by eliminating units and expressing system quantities as diminution-less ratio of quantity in per unit is equal to actual quantity divided to base value of quantity. A well-chosen per unit system can minimize computational efforts, simplify evaluation, and facilitate understanding of system characteristics. Some base quantities may be chosen independently and quite arbitrarily, while others follow automatically depending on fundamental relationships between system variables. Normally, the base values are chosen so that the principal variables will be equal to 1 per unit under rated condition. Per unit system for the stator quantities. The universal practice is to use the machine rating as the base value for the stator quantities. Thus, the following base quantities is chosen for the stator, denoted by subscript S. ES base is peak value of rated line to neutral voltage V. IS base, peak value of rated line current A. F base is rated frequency hertz. This is ampere, this is volt, and this is hertz. The base values of the remaining quantities are automatically set and depend on the above as next slide. You see, omega base is equal to 2 pi F base. Electrical radians per second. Omega M base is equal to omega base multiplied to 2 divided to PF parenthesis mechanical radians per second. ZS base is equal to ES base per IS base. Ohm. LS base is equal to ZS base divided to omega base. Henries. Psi S base is equal to LS base multiplied to IS base is equal to ES base divided to omega base Weber per. And three-phase volt ampere base is equal to 3 RMS base multiplied to I RMS base is equal to 3 multiplied to ES base multiplied to IS base divided to 2. That is equal to radical 2 multiplied to radical 2 is equal to 3 per 2 multiplied to ES base IS base volt amperes. And finally, torque base is equal to T-phase volt ampere base divided to omega m base is equal to 3 per 2 multiplied to PF per 2 multiplied to psi s base multiplied to IS base Newton meters. Newton meters. Per unit stator voltage equation. From equation 3.70, it is equal P psi d minus psi q omega r minus R A I D. Gliding tau out by ES base and noting that ES base is equal to IS base plus IS base multiplied to ZS base is equal to omega base multiplied to psi s base. We get ED divided to ES base is equal to P parenthesis 1 per omega s base multiplied to psi d per psi s base minus psi q per psi s base multiplied to omega r per omega base minus RA per Z S base multiplied to ID per IS base is equal to E T super bar, that is super bar, is equal to 1 omega base P psi d super bar minus psi q super bar omega r super bar minus R A super bar I E super bar. For the purpose of defining unit values and showing a relationship to the values in natural units, a super bar dash will be used to identify per unit quantities. We will, however, drop this convention for subsequent general use to simplify the notation. Okay. Of this slide, I cannot ready for you, so I continue with my book. Okay, I set you until equation 3.83. So, the unit of time in the above equation is seconds. Time can also be expressed in per unit or radians, with the base value equal to the time required for the rotor to move 1 electrical radian, and synchronous speed T base is equal to 1 per omega base is equal to 1 per 2 pi f base. Timing per unit equation 3.83, that is equation may be written as so you see ED is equal to E psi D minus psi Q omega minus RAID. That is, all of the quantity are per unit. Comparing equation 3.70 and equation 3.85, we see that the form of the original equation is unchanged when all quantities involved are expressed in per unit. Similarly, the per unit forms of equation 3.71 and 3.72 are EQ and E0. Per unit time, derivative E appearing in the above equation is given by D is equal to D dt is equal to 1 per omega base multiplied to d per dt, that is equal to e per omega base. Per unit rotor voltage equation is very important. Because rotor is different with stator. From equation 3.70, dividing tau out by EFT base is equal to omega base, psi FT base is equal to ZFT base multiplied to IFT base. The per unit field voltage equation may be written as, so FT is equal to P psi FT plus RFT IFT. Similarly, because of the voltage of damping winding is 0, so we have per unit forms of equation 3.51 and 3.52 R is this form. That is, 0 is equal to P psi KD plus RKDI KD. And the equation 3.91 is this. The above equation showed the form of the rotor circuit voltage equations. However, we have not yet developed a basis for the choice of the rotor base quantity. Stator flux linkage equation. You see the equation of full linkage, but they are per unit quantity. So psi d is equal to psi d per unit is equal to minus LD ID, that they are all of the quantities in per unit. That psi space is equal to L space multiplied to I space. So psi E in per unit and psi q is in per unit and psi 0 in per unit is equal to this equation that you it's very simply city. The definition LAFT is equal to LAFT multiplied to IFT base divided to L space I space, and similar to rotor flux linkage equation. In similarly, in per unit form equation become psi ft, psi kd, and psi kq. You see in the equation of 3.98, 3.99, and 3.100. That all of the value in this equation are per unit. You see LFDA is equal to 3 per 2 multiplied to LAFT per LFT base. That they are the value of per unit of LFTA. I appropriate to choose of per unit system, we have eliminate the factor 3 per 2 in the rotor flux equation. However, we have not yet heard on the values of the rotor base voltage and current, which we will proceed to do next. So, per unit system for the rotor. We said until now about stator, but if we want to say about rotor, we must consider all of the condition. So for per unit system for the rotor, we must consider A, B. Rotor circuit based quantities will be chosen so as to make the flux linkage equation simple by satisfying the following. A per unit mutual inductances between different windings are to be reciprocal. For example, LAFD is equal to LFDA. This will allow the synchronous machine model to be represented by equivalent circuits. 2 or B, all per unit mutual inductances between stator and rotor circuits in each axis are to be equal. For example, LAFD is equal to LAKD. Okay, in per unit. In order to have LFAD equal to LKDF, so that reciprocity is achieved from equation 3.102 and 3.104 is necessary to have. That you see, LKD base I power 2 LD base is equal to LFD base multiplied to IFD base power 2. Multiplying by omega base gives omega is multiplied to LKD base multiplied to IKD base power 2 is equal to omega base multiplied to LFD base multiplied to IFD base power 2. Since omega base L base I base is equal to E base, so we have the equation that the equation is EKD multiplied to IKD is equal to EFD base IFD base. That's volt ampere per volt ampere. Therefore, in order for the rotor circuit mutual inductances to be equal, their volt ampere bases must be equal. For mutual inductances per unit LAFD and LAFDA to be equal from equation 3.95 and LAFD multiplied to IFD base divided to L space I space is equal to 3 pair 2 multiply to LAFD multiply to I space pair LFD base multiply to IFD base. Multiplying by omega base and noting that omega Li is E, we get EFD base multiplied to IFD base is equal to 3 divided to 2 multiplied to ES base multiplied to IS base, that is equal to 3 phase volt ampere case for stator. That's very important, this equation. And similarly, in order for LAKD, that EKD base multiplied to IKD base is equal to 3 divided to 2 ES base IS base. This equation simply that is ordered to satisfy requirement above the volt ampere base in all rotor circuit must be the same and equal to the stator 3-phase volt ampere base. So far, we have specified only the produce of base voltage and base current for the rotor circuit. The next step is to specify either the base voltage or the base current for these circuits. Stator step inductance LD and LQ are associated with the total flux linkage to ID and IQ representatively. So, linkage inductance in the two axes are nearly equal, noting the leakage inductance Li and the mutual inductances LAD and LAQ, that LD is equal to L plus LAD and LQ is equal to LL plus LAQ. Therefore, IFD base is equal to LAD per LAFD multiplied to IS base, and IKD base is equal to LAD per LAKD IS base. This completes the choice of rotor base quantities. As stated before, the per unit system used here is referred to as the LAD base, reciprocal per unit system. In this system, the base current in any rotor circuit is defined as which indices in each phase per unit voltage equal to per unit LAD, that is the same voltage as balanced three-phase unit peak armature current. So, per unit power and torque for a synchronous machine in the rotor is written by the equation 3.160. That is, PT is equal to ED/ID plus EQ/IQ plus 2E0I0. And similarly, for base torque, we have the equation 3.170. Alternative per unit system and transformation. Okay. Are you okay, student? It's set to until this slide, until equivalent circuit for direct and quadrature axis. Okay, you see this I read for you about alternative per unit system and transformation. Several different alternative per unit system have been proposed in the literature for the analysis of synchronous machine. Some analyses, notable Lewis, have also suggested the use of an alternative form of transformation from the ABC refer frame to the PQ0 reference frame, which is similar to that of equation 3.59, but with factors AD and AQ equal to radical 2 per 3 instead of 2 per 3, and with zero sequence coefficient equal to 1 per radical 2. The alternative transformation equation are given by. You see the PQ0 transformation by the another coefficient AD and AQ. And the inverse transformation is obtained by this equation. Such a transformation is orthogonal, i.e. the inverse of the transformation matrix is equal to its transpose. This also means that the transformation is power invariant. ET is equal to EAIA plus EBIB plus ECIC. That is equal to EDID plus EQIQ plus E0I0. In addition, with this transformation, all mutual inductances would be reciprocal. However, as discussed in reference 19 by Harris, Lorenson, and Stephens, such a transformation has several fundamental disadvantages which appear to override the advantage. The orthogonal transformation does not correspond to any particular meaningful physical situation. KD and KQ equal to radical 2 per 3, the equivalent D and Q axis coils would have radical 3 per 2 times the number of terms as ABC coils. This removes the unit-to-unit relationship between ABC and PQ zero variables that exist with the original transformation of equation 2.59. So, reference 19 provides a thorough and comprehensive analysis of the alternative per unit and transformation system. It concludes that the transformation of equation 3.59 together with the LAD is a reciprocal per unit system leads to a system which reflects most closely the physical future of the machine. In addition, the inductances in the resulting equivalent circuits correspond to those normally calculated by machine designers. In view of this advantage, this system is widely used by the electrical utility industry and generator manufacturers. So, F base is rated frequency, I space is peak line current per amperes, Z space is E space per I space per O, omega base, omega M base is similar to before equations. H means Henry's and omega space is per Weber term. So rotor base quantities obtained by this equation that you see. You must divide the actual value per base value. Okay? Divide the two base value. So, complete set of electrical equation in per unit in view of the LAD base per unit system chosen in per unit. That in per unit we have AFD is equal to LF, EA is equal to LAKD is equal to LKDA is equal to LAD. That is very simply by for me. In the following equation, 2Q axis amortisseur circuit are considered and the subscript 1Q and 2Q are used in place of AQ to identify them. Only one P-axis amortisseur circuit is considered and is identified by subscript 1D. Since all quantities are in per unit, we drop the superbar notation. At per unit, stator voltage equation is equal to is obtained by this equation, and per unit rotor voltage equation is obtained by this equation. And per unit stator flux linkage equation is obtained by this equation. And so per unit rotor flux linkage equation is obtained by this formula. Okay, and so we can calculate the reactance by having the frequency. So the frequency of the stator quantities is equal to the base frequency. The per unit reactance of a winding is numerically equal to the per unit inductance. For example, XD is equal to 2 pi F multiplied to LD. And dividing by Z space, so XD per Z space is equal to F per F base multiplied to LD per LS base. If F is equal to F base, per unit value of XD and LD are equal. For this reason, in the literature on synchronous machine, symbols associated with reactances are often used to denote per unit inductances. Okay, student, I said to you until the chapter 3, the page 88, until equivalent circuits for direct and quadrature access. Please study this lecture at home, and if you have any question, I try to answer to you. So if you have any question, I'm ready. But if you don't have any question, you can exit of the class. And shukran for everybody. Thank you for you. Thank you. Thank you. Bye, student. Thank you. Shukran.